So remember, Kirchoff's law says when you sum all of the currents into a branch, that must be equal to all of the currents leaving the branch. So the branch that I'm going to focus on is at node C. So let's look at the currents. So cleaning this up a little bit so we're not distracted, notice how we have the two currents going into node C, currents 1 and 2, and that must be equal to the currents leaving node C, and that is current 3. So here is our third equation. Let's rewrite our other two independent equations. The first one we found from Kirchoff's law was the EMF of loop 1 minus 2I1R plus 2I2R minus the EMF of battery 2 is equal to 0. Well, we could simplify this to say, let's see, we could combine the two EMFs, so that's minus the EMF, and we can factor out a 2R from both resistors, and that is going to give us a I1 minus I2 is equal to 0. And let's just isolate I1 and I2 on one side of the equality. We have I1 minus I2 is equal to minus the EMF over 2R. Or if we didn't want to deal with the negative sign, we can multiply through. But I'll leave this as is right now. So let's call this equation 4. Now the second independent equation we found, equation 2, said the EMF minus 2I1R minus I3R is equal to 0. Well, let's isolate I1 and I3. So in isolating I1 and I3, I see that I could write 2I1R plus I3R is equal to the EMF of battery 1. Factoring out an R, or dividing both sides by R, we have 2I1 plus I3 is equal to the EMF of battery 1 over the resistance. Let's call this equation 5. And then the final equation is I1 plus I2 is equal to I3. This was just equation 3. So let's look at equations 3 and 4 and add them together. For those of you in linear algebra, I know that you know how to do this using matrices, but I'm going to assume we haven't had linear algebra yet, and I'm just going to use the elimination method that I've learned for solving for multiple independent equations. Notice in equation 4, I have the difference, I1 minus I2. Equation 3, I have the sum of I1 plus I2. Let's add those two equations together. So equation 4 is I1 minus I2 is equal to minus the EMF over 2R. Let's sum these by the columns. So I see that the I2's cancel, leaving me with 2I1 is equal to I3 minus the EMF of battery 1 over 2R. Let's go ahead and put that I3 on the left-hand side of the equality. So we have 2I1 minus I3 is equal to minus the EMF over 2R. So notice what we have here. We'll just go ahead and call this equation 6. And look at equation 5. Equation 5 has a 2I1 plus I3, while equation 6 has a 2I1 minus I3. So let's do this. Let's take equation 5 and add it to equation 6. So I'll start off by just writing equation 5, 2I1 plus I3 is equal to EMF of battery 1 over R. And then let's write equation 6, 2I1 minus I3 is equal to minus the EMF of battery 1 over 2 times the resistance of resistor 2. When we sum these together, notice that the current 3 cancels. So what we have is 4I1 is equal to the EMF over the resistance minus the EMF over twice the resistance. On the right-hand side, this is just equal to the EMF over twice of the resistance. So what we now have for current 1 we get that current 1 is equal to the EMF of battery 1 over 8 times the resistance of resistor 2. So I noticed my units on this will check because the unit for current can be expressed in a volt per ohm. So the EMF of the battery is the volt, the resistance is in ohms. So my result works. And notice also how this current is a positive current because the EMF of battery 1 is a positive EMF, the resistance is positive, so my current is positive. What this means is I chose the correct direction for current 1.